Have you ever stared up at the night sky and wondered how it all began? We're not just talking about stars and galaxies. We're talking about the very first flicker of existence itself. What sparked the cosmos into being? What danced in the darkness before space and time as we know them were even born? These aren't just questions for philosophers or physicists. They tug at something deep within all of us, a shared curiosity about our place in this vast, mysterious universe. Today, we're setting off on a journey back to the very beginning, to a moment so profound and elusive that it challenges everything we think we know about reality. We'll be exploring 30 incredible theories about the universe's first particles, the tiny building blocks that set everything in motion. From cosmic strings to quantum foam, from brains colliding in higher dimensions to particles popping in and out of existence in the blink of an eye, these ideas aren't just wild speculation. They represent humanity's boldest attempts to peel back the layers of time and glimpse the birth of everything. And the best part, you don't need a degree in theoretical physics to come along for the ride. We're breaking down these mind-bending concepts into stories, each one a piece of the grand puzzle of creation. So get comfortable and open your mind, because what you're about to hear will stretch your imagination in ways you never thought possible. We're going to explore ideas that question the nature of reality, alternate universes, and what it truly means for something to come from nothing. This isn't just a list of theories, it's an invitation to wonder, to get lost in the possibilities, and to rediscover that childlike awe we all feel when we look up at the stars. Ready to begin? Let's dive in. Our journey begins with the most famous origin story of all, the Big Bang Singularity. Picture everything you've ever known, every star in every galaxy, every atom in your body, all compressed into a single point of infinite density and temperature. This is the singularity, the moment zero from which our universe is said to have exploded into existence. For decades, this has been the cornerstone of modern cosmology, a powerful image that captures the sheer violence and wonder of cosmic birth. But what does infinite density really mean? Think of it like this. Try to imagine squeezing the entire mass of the universe into a space smaller than a single atom. The laws of physics as we know them simply break down. Gravity becomes so intense that space and time themselves lose all meaning. It's a concept so extreme that it pushes our understanding to its absolute limit. This is precisely why the singularity is such a compelling yet deeply problematic idea. It's less of a full explanation and more of a placeholder for our ignorance, a mathematical boundary where our current theories give up. From this impossible state, the universe began to expand and cool. In the first fleeting moments, a searing hot soup of energy and the universe's very first particles started to take shape. Protons, neutrons, and electrons, the building blocks of all ordinary matter, wouldn't appear until a few minutes later. But those first particles, entities like quarks and gluons, began to condense out of the pure energy of the newborn cosmos. This is the primordial state that set the stage for everything to come. Yet for all its grandeur, the Big Bang Singularity theory leaves us with profound questions. What caused the singularity to suddenly expand? What existed before it? The theory describes the aftermath with incredible precision, but it says nothing about the ignition itself. It's like hearing the roar of an engine but having no idea what sparked it to life. This limitation is why physicists have been driven to look for deeper, more complete explanations for those first particles. The singularity isn't the end of the story. It's the doorway to a much stranger and more fascinating set of possibilities. But if the singularity is a door, then cosmic inflation is the key that unlocks it. This theory, pioneered by physicist Alan Guth, takes those first unimaginable moments and gives them a breathtaking new context. Instead of a simple explosive expansion, inflation suggests that the universe underwent a period of hyper-fast, exponential stretching, faster than the speed of light itself, in the first tiny fraction of a second after the Big Bang. This wasn't just an expansion of matter into space, it was a rapid stretching of spacetime itself, smoothing out the cosmos and seeding it with the potential for everything to come. To grasp this, picture a tiny, subatomic speck of the early universe, a region so small it could have been perfectly uniform in its energy and density. Then, driven by a peculiar state of energy known as a false vacuum, this speck underwent a phenomenal growth spurt. In less than a trillionth of a trillionth of a trillionth of a second, it doubled in size over and over again, inflating to become larger than our entire observable universe today. This incredible process explains so much. It tells us why the universe appears so flat and uniform in every direction we look, because it was once a tiny, connected region that got stretched to cosmic proportions. But inflation's most profound gift was its ability to create something from almost nothing. Even in that tiny, ultra-smooth initial speck, the rules of quantum mechanics tell us there would have been tiny, unavoidable fluctuations, a quantum fizz of particles popping in and out of existence. As inflation stretched the universe, it also stretched these minute quantum jitters, magnifying them from the subatomic scale to the astronomical. These stretched-out ripples in the fabric of spacetime became the blueprints for the entire cosmic structure we see today. The slightly denser regions in this cosmic imprint would, over billions of years, pull in more and more matter through gravity, eventually giving birth to the first particles clumping together, then stars, galaxies, and vast galactic clusters. In this way, cosmic inflation is more than just an add-on to the Big Bang. It's the mechanism that explains how the pristine conditions of the singularity could have given rise to a universe filled with complex structure. It provides a physical process that turns the mysterious ignition of the cosmos into a dynamic, testable event. The quantum fluctuations that created the seeds for galaxies were also the very seeds for the first long-lasting particles to condense out of the energy sea. Without this period of hyper-fast stretching, the universe might have remained a smooth, featureless soup, never cool enough or varied enough to form the building blocks of atoms, planets, or life. Inflation gave the cosmos its texture and its history, setting the stage for the grand narrative of evolution that followed. Yet if inflation gave us the mechanism, it still relied on that initial speck of uniform energy. So where did that come from? To answer that, we must venture into one of the most profound and counterintuitive ideas in all of physics: the possibility that the entire universe could have sprung from absolute nothingness due to the bizarre rules of quantum mechanics. This isn't just empty space, we're talking about a complete and total void, no matter, no energy, not even space or time. At the human scale, the idea of getting something from nothing is absurd. It violates every instinct we have about cause and effect, but the quantum world operates by a completely different set of rules. Here, uncertainty is a fundamental principle. We can see this at play in the phenomenon of virtual particles. Even in what we consider a perfect vacuum, pairs of particles and antiparticles spontaneously flicker into existence, borrowing energy from the void for an impossibly brief moment before annihilating each other and returning the energy. They are a temporary violation of conservation of energy permitted by the fuzzy math of quantum uncertainty. Now, imagine if one of these fleeting quantum fluctuations, instead of instantly disappearing, was somehow stabilized and amplified on a cosmic scale. The theory suggests that a particularly large fluctuation in this quantum foam of spacetime could have been triggered, pinching off a tiny bubble of energy. In this scenario, the universe wouldn't have expanded into anything. It would have been the rapid creation of space itself from that initial pinprick of reality. The energy borrowed from the quantum vacuum for that initial fluctuation was ultimately balanced by the gravitational energy of the entire expanding universe, meaning the total energy of the cosmos could very well be zero. This transforms our understanding of nothing. Quantum nothingness isn't an inert emptiness, it's a seething, bubbling cauldron of potentiality, constantly birthing and destroying ephemeral entities. The universe, then, might be the ultimate free lunch, the one fluctuation that didn't cancel itself out. It's a concept that stretches the limits of our language and logic, pointing toward a reality where existence is not the default state but a magnificent, statistically improbable exception that somehow became permanent. But to go even deeper than the quantum vacuum, to truly touch the moment of ignition, we must venture into the most extreme environment physics can conceive, the Planck epoch. This is the universe's first fleeting moment, a duration so short it defies imagination, just 10 million trillion trillionths of a second after the Big Bang. In this almost mythical interval, the energy and density were so fantastically high that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were fused into a single, unified superforce. The universe operated under a law we have not yet discovered, a theory of everything that seamlessly blends Einstein's general relativity with the quantum world. In this furnace, the very concepts of particles, space, and time as we understand them cease to have meaning. Particles as we know them, like electrons or quarks, simply could not exist. They would be instantly torn apart and reabsorbed into the energetic whole. Instead, reality was likely a chaotic, seething ocean of potentiality that physicists call quantum foam or spacetime foam. Picture the surface of a bubbling pot of water, but where each bubble is a temporary, tiny universe flickering in and out of existence. The fabric of spacetime itself would have been tumultuous and frothy, with tiny wormholes and tunnels constantly forming and collapsing, connecting and disconnecting in a frenzied dance. This foam isn't made of anything material. It is the primal texture of reality itself, a manifestation of the inherent uncertainty dictated by quantum mechanics applied to gravity. Within this foam, the seeds of all subsequent matter were sown. The intense fluctuations in energy and curvature throughout this frothy landscape were the ultimate origin of the quantum fluctuations that inflation would later magnify. A slightly more persistent bubble in this foam, a region of slightly lower energy, could have been the trigger for the cosmic inflation that launched our entire universe. So, in a very real sense, the quantum foam of the Planck epoch is the canvas upon which the first brushstrokes of existence were painted, a chaotic and creative void from which everything we know somehow crystallized into being. But to move beyond the chaotic foam of the Planck epoch, we need a framework that can actually describe it, a set of equations that can handle such extreme conditions without breaking down. This is where we encounter one of the most elegant and ambitious ideas in modern physics, string theory. While the previous theories try to explain the conditions for the first particles, string theory redefines what a particle is at the most fundamental level. It proposes a radical departure from the standard models point-like zero-dimensional particles. Instead, the fundamental building blocks of reality are unimaginably tiny, one-dimensional loops or strands of pure energy vibrating strings. To grasp this, forget everything you know about solid little balls of matter. Picture instead a string on a guitar. When you pluck it, it vibrates at a specific frequency, and that vibration produces a distinct musical note. Now imagine that every single particle in the universe is just a different note on a cosmic instrument. An electron isn't a tiny dot, it's a string vibrating at one specific frequency. A quark is that same string vibrating at a different, higher frequency. A photon of light is yet another vibrational pattern. In this breathtaking vision, the entire symphony of the cosmos, all matter and all forces, is composed from the harmonies of these microscopic strings. The implications for the universe's first moments are staggering. In the searing heat of the Big Bang, these strings would have been vibrating with unimaginable energy, their patterns constantly shifting and changing. The familiar particles we know would have been unable to hold their form, melting back into a chaotic orchestra of fundamental vibrations. String theory provides a potential glimpse into that Planck epoch, a realm where the very idea of a distinct particle blurs into a spectrum of energetic resonance. It suggests that the first particles were not things, but rather the most stable, dominant vibrational modes to emerge as the universe cooled, the foundational notes that eventually defined the laws of physics for our cosmic realm. For this elegant mathematics to work, however, string theory demands a dramatic expansion of our reality. The 3 dimensions of space and 1 of time that we experience are not enough to accommodate all the required vibrational patterns. The theory only achieves consistency in a universe with 10 or even 26 dimensions. This means the vast majority of dimensions are curled up, or compactified, into a space so tiny that they are completely hidden from our perception, much like how a garden hose looks like a one-dimensional line from a distance but reveals a 2-dimensional surface upon closer inspection. The specific way these extra dimensions are folded determines the properties of the particles in our observable universe, effectively writing the laws of physics through geometry. This offers a profound new answer to the question of why our universe has the specific constants and forces that it does. It wasn't chosen at random. It's a direct consequence of how the hidden dimensions curled up as the early universe cooled and expanded. In the frantic moments of creation, countless different compactifications might have occurred, potentially giving rise to a multiverse of different universes, each with its own unique physical laws. Our universe, with its perfect balance for allowing atoms, stars, and life to form, is simply one of many possible cosmic melodies that sprang from the string's initial vibration, a single tune in an infinite symphony of existence. Now, if string theory gives us the stage and the instruments, supersymmetry provides one of the most beautiful and haunting melodies that could have been played upon it. This theory introduces an astonishing level of order and partnership into the quantum world, proposing a truly elegant symmetry that, if true, would have been absolutely fundamental to the behavior of the universe in its first, most energetic moments. The core idea is as simple as it is profound. For every known particle in the Standard Model, every electron, every quark, every photon, there exists a hidden, super-heavy partner particle. Physicists call these hypothetical partners sparticles. The electron's partner is the selectron. The quark's partner is the squark. Even the force-carrying particles get counterparts. The photon's partner is the photino. This isn't just a whimsical naming convention. It represents a deep mathematical symmetry that many theorists believe is essential for a complete theory of the fundamental forces, particularly for unifying the quantum world with gravity. In the pristine, ultra-high-energy environment immediately following the Big Bang, this symmetry would have been perfect and unbroken. Ordinary particles and their sparticle twins would have been indistinguishable, 2 sides of the same coin, existing in a state of perfect balance. This has a breathtaking implication for the origin of matter. In that scorching hot early universe, the incredible density of energy would have been more than enough to mass produce these super-heavy sparticles in enormous numbers. It's likely that the cosmos wasn't filled with the familiar protons and neutrons we're made of, but was instead dominated by a thick, exotic soup of selectrons, squarks, and photinos. These sparticles would have been the universe's first stable, massive inhabitants, the primary form of matter when everything was still too energetic for our familiar particles to exist for more than a fleeting instant. But as the universe continued to expand and cool at a ferocious rate, the perfect symmetry between particles and sparticles would have broken. Think of it like water freezing into ice. While liquid, water molecules are symmetric and uniform, but as it freezes, that symmetry is broken and a crystalline structure emerges. In a similar cosmic phase transition, the sparticles, being inherently much heavier, became unstable. One by one, they began to decay, transforming into the lighter, more stable particles we now recognize as the building blocks of our world. This decay process wasn't just a simple disappearance. It was a transformation, a forging of the ordinary from the extraordinary. The decay of these superpartners could have been the primary factory that produced the first long-lasting quarks and electrons, essentially gifting the universe the raw ingredients for all future atoms. There's another compelling reason physicists are so drawn to this idea. One of the biggest mysteries in cosmology is the identity of dark matter, the invisible, mysterious substance that makes up about 85% of all the matter in the cosmos and whose gravitational pull holds galaxies together. A leading candidate for what dark matter actually is, the lightest particle, theorists suggest that when the Great Decay happened, the lightest of these superpartners would have had nothing lighter to decay into, making it stable. Billions of these particles, left over from the first moment of creation, could be drifting through you and everything around you right now, their collective gravity sculpting the large-scale structure of the universe itself. So supersymmetry doesn't just explain the origin of ordinary matter, it might also simultaneously solve the deepest mystery of what most of the universe is actually made of. But to truly understand how those first particles gained the substance to form the world we know, we must turn to one of the most celebrated discoveries in modern physics, the Higgs field. Imagine the newborn universe as an immense, invisible ocean of energy. In its earliest, hottest state, this ocean was perfectly calm and symmetrical. Every particle, every quark, every electron, every force carrier was like a photon of light, zipping through this ocean at the speed of light itself, utterly weightless. They had energy, but they had no mass. For the universe to become structured, for particles to slow down and clump together to form atoms, stars, and us, something profound had to happen. That something is known as the Higgs mechanism. The Higgs field is not like a magnetic or gravitational field you can measure with an instrument. It is more like a fundamental property of space itself, an energy field that pervades every single cubic inch of the universe, even in what we call a perfect vacuum. The crucial idea is how different particles interact with this omnipresent field. Some particles, like photons, simply don't interact with it at all. They sail through completely unimpeded, which is why they remain massless and forever travel at light speed. But other particles do interact with it, and how strongly they interact determines their mass. A helpful, though imperfect, analogy is to think of a famous person walking through a crowded room. The crowd represents the Higgs field. If an unknown person walks through, they move quickly and easily. Barely interacting with the crowd, they are like a photon, nearly massless. But if a beloved celebrity enters, people immediately swarm around them. Their movement is slowed and hindered by these constant interactions. This difficulty moving, this inertia, is the analog of gaining mass. The celebrity isn't intrinsically heavy. Their mass is acquired through their interaction with the environment. In the same way, an electron gains its specific mass by constantly interacting with the Higgs field that fills all of space. The moment this mechanism switched on in the early universe was a cosmic event of staggering importance, a phase transition often called the electroweak epoch. For a fleeting instant after the Big Bang, the electromagnetic force and the weak nuclear force were unified as a single, symmetrical force. Particles like the W and Z bosons, which today are massive carriers of the weak force, were massless and indistinguishable from photons. But as the universe expanded and cooled to a temperature of around 1,000 trillion degrees, roughly a picosecond after the Big Bang, the cosmos reached a critical threshold. The Higgs field, which had been in a high-energy, symmetrical state, suddenly dropped into its lowest energy state, like water crystallizing into ice. This process, known as spontaneous symmetry breaking, fundamentally altered the fabric of reality. As the Higgs field settled into this new state, it instantly endowed certain particles with mass. The W and Z bosons suddenly became very heavy, which effectively shortened their range and cleaved the unified electroweak force into the two distinct forces we observe today, the short-range weak force and the long-range electromagnetic force. Quarks and electrons gained their specific tiny masses. This was the moment the first truly massive particles were born. Before this transition, particles were ethereal, weightless entities. Afterward, they had substance. They could slow down. They could feel the tug of gravity and begin the long process of clumping together. The properties of every single atom in your body were irrevocably set in motion by the specific strengths with which their constituent particles coupled to this universal Higgs field. This discovery answers a foundational question. Mass is not an intrinsic property handed down from the Big Bang. It is an acquired characteristic, a gift from an invisible cosmic field that gives the universe its structure and diversity. Without the Higgs mechanism, there would be no atoms, no chemistry, no planets, and no life. We would live in a universe of fleeting, massless particles racing through an eternal, featureless night. The Higgs field is the silent, invisible architect of substance, the reason there is something rather than nothing in the form we recognize. Yet for all the structure given by the Higgs field and supersymmetry, a far more fundamental puzzle was already encoded into the universe's earliest particles, a shocking and overwhelming preference for matter over antimatter. This isn't just a minor imbalance, it is the single most important reason you and everything you see exists at all. According to all our best theories, the Big Bang should have created matter and antimatter in perfectly equal amounts. For every quark born, an antiquark should have appeared, for every electron, a positron, and in the searing heat of those first moments, these particle-antiparticle pairs would have continuously collided and annihilated each other in a storm of pure energy, leaving behind absolutely nothing but a fading flash of light, a universe devoid of any lasting substance. But that's clearly not what happened. Our universe is filled with galaxies, stars, planets, and life, all made from matter. So what happened to all the antimatter? This profound mystery is known as the problem of baryogenesis, and solving it requires a fundamental breaking of nature's most perfect symmetries. The Russian physicist Andrei Sakharov outlined 3 essential conditions that must have been violated in the early universe to create this matter-dominated reality. First, the processes at work had to violate the conservation of baryon number, meaning they could actually produce more quarks, the building blocks of protons and neutrons, than antiquarks. Second, they had to occur during a period when the universe was out of thermal equilibrium, a moment of chaotic change where these new rules could take effect without being instantly reversed. And third, and perhaps most strangely, they had to violate both charge conjugation and parity symmetry. Let's unpack that last one, known as CP violation. Charge conjugation symmetry, or C-symmetry, means the laws of physics should work exactly the same for a particle as they do for its antiparticle. Parity symmetry, or P-symmetry, means physics should be identical if you look at everything in a mirror universe where left and right are swapped. For a long time, physicists believed nature perfectly respected both these symmetries, but experiments revealed that this isn't entirely true. In the subtle decay of certain exotic particles called kaons and B-mesons, we observe a tiny 1% level preference for matter over antimatter. It's as if the universe has a barely perceptible left-handed bias, a fundamental favoritism written into the fabric of reality itself. While the CP violation we've observed in labs is far too small to account for the vast cosmic imbalance we see today, it provides a crucial proof of concept. The laws of physics are not perfectly symmetrical. They contain the very crack needed to explain our existence. Theorists propose that in the extreme energy of the very early universe, this effect would have been vastly magnified by new, heavier particles or unknown forces. Grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces, often predict the existence of super-heavy particles called X-bosons. As the universe cooled and these X-bosons decayed, their decay mechanisms could have inherently favored the production of quarks over antiquarks by just 1 part in a billion. That minuscule excess was all it took, after the storm of annihilation finished, where every particle met its antipartner and destroyed it. that 1 in a billion surplus of matter was all that remained. Every single atom in our observable universe is the legacy of that tiny, precious imbalance, the ash left over after a near-perfect cosmic fire burned itself out. The quest to find the source of this asymmetry is more than just an academic exercise. It is a search for the ultimate reason why there is something rather than nothing. It drives experiments in massive particle colliders and observations of the deepest cosmos, all trying to catch nature in the act of revealing its inherent bias, the secret preference for existence that allowed our universe to be born. This idea of a single, finely tuned universe emerging from the chaos, however, leads us to one of the most expansive and mind-bending concepts in all of cosmology, the inflationary multiverse. We already discussed how cosmic inflation could have smoothed and seeded our entire observable universe. But what if that process of hyper-fast stretching didn't just happen once and then stop? What if it's an eternal, ongoing phenomenon, a fire that ignites new universes without end? This is the heart of the inflationary multiverse theory, a vision where our entire cosmos is just one bubble in a vast, endlessly frothing cosmic ocean. The mechanism hinges on the nature of the energy field that drove inflation, known as the inflaton field. Think of this field like a landscape of hills and valleys. The high-energy, unstable state that triggers rapid expansion is like a ball perched precariously at the very top of a steep hill. This is the false vacuum state. Naturally, the ball wants to roll down into a valley which represents a lower energy, stable state. This is the end of inflation for that region of space, what we call the true vacuum. When that roll happens, the immense energy stored in the field is released, heating the region into a hot Big Bang and creating a universe like our own. But here's where it gets incredible. Due to quantum fluctuations, this roll down the hill doesn't happen everywhere at once. Picture a vast mountainside covered in fog. In one tiny patch, the fog clears and the ball rolls down, creating a stable, calm valley. That's our universe beginning. But elsewhere in the immense fog, the ball is still perched high on the hill. And because inflation is stretching space-time itself faster than light, those high-energy regions are expanding exponentially, becoming vastly larger than the bubbles where inflation has ended. Within these still inflating regions, quantum effects will continuously spawn new, random patches where the ball rolls down into a valley, each one a new Big Bang, each one a new universe pinching off from the inflating background. This process becomes self-perpetuating, eternal, creating an infinite number of these disconnected bubble universes. Now, the true magic and the profound implication for our first particles lies in the nature of those valleys. The stable state our universe rolled into gave us a specific set of physical constants: the mass of the electron, the strength of gravity, the nature of the nuclear forces. But what if the landscape of possible valleys is enormous? In string theory, for instance, the way the extra dimensions curl up could create a virtually limitless number of different stable states, each one with a completely different set of physical laws. This concept is known as the string theory landscape. In this eternal inflationary sea, every single possible valley, every possible set of physical laws would eventually be realized in some bubble universe. This completely transforms our perspective. The specific first particles that condensed in our universe, quarks with their precise masses, electrons with their exact charge, are not special or inevitable. They are simply the unique combination that emerged from our particular bubble's transition. In the universe next door, inflation might have ended in a valley where the Higgs field is much stronger, giving all particles tremendous mass and creating a universe that is incredibly dense and short-lived. In another, the strong nuclear force might be too weak to bind protons and neutrons together, making atoms impossible and ensuring a cosmos filled only with hydrogen and chaos. Some universes might have more than 3 spatial dimensions, altering the very nature of gravity and motion, while others might have forces that we cannot even begin to imagine. Our universe, with its perfect balance that allows for galaxies, planets, and life, is not a planned outcome. In this vast multiverse, it is simply a statistical inevitability. With an infinite number of bubbles, every possible set of laws, no matter how improbable, will appear somewhere. We find ourselves in one of the rare habitable bubbles, not because it was designed for us, but because we could not possibly exist in the overwhelming majority of others. The first particles in our history were not the first particles in a grand cosmic sense. They were merely the first particles in our story, one variation in an infinite tapestry of cosmic possibilities. This idea doesn't diminish our existence. It elevates the incredible, fragile luck of our particular universe's recipe, a recipe that began with those first, fleeting vibrations in the energy of our specific bubble. While the multiverse offers a breathtakingly vast canvas for cosmic possibilities, another theory brings our focus back to a single, profound event at our own universe's beginning, offering a radical alternative to the daunting concept of a singularity. This is the idea of the Big Bounce, a cornerstone of the theory known as loop quantum gravity. Instead of a definitive starting point of infinite density, this framework suggests our universe might not have been born from nothing, but rather reborn from the death of a previous cosmic era. Imagine the entire universe contracting in a devastating Big Crunch, but rather than collapsing into a meaningless singularity, the very fabric of space-time resists, reaching a point of maximum density before springing back into a new expansion, a glorious cosmic rebound. Loop quantum gravity provides the physical mechanism that makes this bounce possible. It approaches the problem of quantum gravity from a fundamentally different angle than string theory. Where string theory adds extra dimensions, LQG quantizes the dimension we know and love, space itself. It proposes that space is not infinitely divisible, not a smooth, continuous backdrop. Instead, it's woven from a fabric of unimaginably tiny, one-dimensional loops, a network of finite threads of gravitational field. Picture a tremendously fine mesh, with each individual loop being a Planck length in size, a scale so small that 1 trillion of these loops could fit across a single atom. This granular structure of space has a stunning consequence. It prevents the infinite collapse predicted by classical physics. In the standard Big Bang model, as we rewind time, the universe gets hotter, denser, and smaller, all heading towards that impossible singularity. But in the LQG universe, as everything contracts, it eventually reaches a density so extreme that it encounters the fundamental graininess of space. The interconnected loops of the quantum spacetime fabric push back against further compression, creating a tremendous repulsive force. This isn't a force in the traditional sense, it's a quantum geometric effect, a fundamental property of how reality is constructed. This repulsive force acts like a cosmic trampoline, halting the collapse and initiating the expansion we now observe as the Big Bang. So what would this transition have looked like? The universe wouldn't have popped into existence from a point. It would have emerged from a supremely dense hot state, a cosmic embryo with a finite physical size. This immediately solves the singularity problem. There is no point of infinite anything, no breakdown of physics. The laws of nature hold throughout the entire process. In this hot, dense quantum state, the very concepts of before and after the bounce become murky. Time, as a classical concept, may have dissolved into a quantum fog, meaning the bounce represents a bridge between two classical universes rather than a clear-cut moment of creation. And from this quantum geometry, the first particles were born. As the universe rebounded and began its rapid expansion, the incredible energy stored in the quantum spacetime fabric had to go somewhere. That energy condensing and crystallizing out of the primordial geometry is what gave rise to the very first quantum fields and their excitations, the particles. The specific vibrational modes of those spacetime loops, the way they interconnected and resonated as the bounce occurred, determined the initial conditions that would later define the matter and forces in our new universe. In this view, particles aren't just things in space, they are manifestations of space, excitations of the same quantum geometric foundation that makes up reality itself. The first quarks, the first electrons, all owe their existence to the specific way the universe rebounded from its previous incarnation, making our entire cosmos a phoenix rising from the quantum ashes of its predecessor. But this grand cycle of cosmic death and rebirth presents an even deeper question, one that pushes the boundaries of physics and philosophy. What, if anything, remains from one eon to the next? If the universe resets to a state of maximum smoothness and low entropy, how could any information or structure possibly survive such a total erasure? Roger Penrose proposes a truly fascinating, albeit highly speculative, answer. He suggests that while all particles, forces, and even the constants of nature might be reset, certain ultra-large-scale information could, in a sense, leak through the conformal boundary. This information isn't carried by particles or energy as we know them, but is instead encoded in the gravitational fabric of spacetime itself, imprinted as subtle anisotropies or patterns in the gravitational field of the new eon. This idea finds a potential and quite astonishing fingerprint in the cosmic microwave background radiation, the afterglow of our own universe's Big Bang. Penrose and his colleagues have analyzed the patterns in this background radiation, searching for signs of impossible circular structures. Their controversial claim is that these concentric rings, areas of unusually uniform temperature, could be the imprints of immensely powerful gravitational waves generated by the collision of supermassive black holes in the previous eon. As the universe approached its conformal boundary, these gravitational shock waves would have been the last significant events to ripple through spacetime, and their pattern could have been stamped onto the smooth initial state of our own eon, like a ghostly echo lasting trillions of years. If this holds any truth, it would mean that the very first particles of our universe did not emerge from total randomness. Their distribution and the initial conditions that led to the formation of the first structures were subtly influenced, perhaps even preordained, by the final, dramatic moments of a cosmos that existed before our own. The quantum fluctuations that inflation amplified were not purely random, they were seeded with a faint cosmic memory. In this view, our universe's first particles and the large-scale structure they eventually formed inherited a legacy from an unimaginably ancient past, making our entire cosmic story not a singular event, but one chapter in an endless, conformally connected book of eons. But what if the stage itself is the final illusion? We've been exploring the actors, the particles, and the play, the forces and laws that govern them. Yet we've always assumed they perform upon a fixed, fundamental stage of space and time. This next theory challenges that very assumption, suggesting that space and time are not the bedrock of reality, but are themselves collective phenomena that emerge from something deeper and far more strange. This is the radical concept of emergent spacetime, an idea that completely rewrites the opening lines of our universe's story. To grasp this, consider a more familiar example of emergence, the temperature of a gas. If you have a single molecule of air, the idea of it having a temperature is meaningless. Temperature isn't an intrinsic property of the molecule. It's a collective property that only emerges from the statistical average of the jittering, chaotic motion of trillions upon trillions of molecules. The molecule is fundamental, but the temperature is emergent. Now, apply this same logic to the fabric of the cosmos itself. What if space-time is not fundamental, but is like the temperature, a large-scale collective illusion that arises from the interactions of countless tiny, fundamental building blocks that operate on a level where the very concepts of here and now have no meaning? The candidates for these fundamental building blocks are numerous and profoundly exotic. Some theories propose a universe built from quantum bits or qubits of information. In this digital physics perspective, the cosmos is essentially a colossal cosmic computer, and every particle, every force, and even the space between them is just a manifestation of information being processed. Other frameworks, like string theory's holographic principle, suggest that all the information within a volume of space is actually encoded on its two-dimensional boundary, like a complex hologram where a three-dimensional image emerges from a flat surface. Our rich three-dimensional experience of the world would, in this view, be a magnificent projection, but perhaps the most tangible approach comes from the world of condensed matter physics. Think about the surface of a lake. It appears to be a continuous, smooth sheet, but we know it's actually made of a vast number of discrete water molecules. Now imagine ripples moving across that lake. Those ripples are waves, but they are also things. They have energy and momentum and can interact. To a hypothetical two-dimensional creature living on the lake's surface, those ripples would be the fundamental particles of its world. It would have no concept of the deep molecular reality beneath it. It would only know the particles that emerge from its medium. This is precisely how some physicists now view our own reality. The smooth, continuous spacetime we perceive might be like the surface of the lake. The fundamental reality could be a vast, chaotic quantum system, a kind of quantum foam, or a network of entangled relationships that exists at the unimaginably small Planck scale. In this frothing foundation, there is no space and no time as we know them, only a tangled web of quantum connections. What we perceive as a particle, like an electron, may not be a tiny billiard ball but an excitation or a ripple in this underlying system, much like a wave on the lake. Its properties, its mass, its charge, its very existence are determined by the specific way this quantum substrate vibrates. This changes everything about the universe's first moments. There was no moment zero because time itself had to condense into existence. There was no point of infinite density because space had to crystallize from this more fundamental network. The Big Bang was not an explosion in space and time, but the very process by which space and time themselves emerged and cooled into the familiar dimensions we experience. In those first instants, the distinction between a particle and a volume of space would have been blurry, even meaningless. The first particles were likely not discrete entities at all, but the most stable, persistent patterns of vibration to coalesce as the cosmic medium cooled and settled, defining the laws of physics as they went. This perspective offers a stunningly elegant solution to the singularity problem. You cannot have a singularity in a place that doesn't yet exist. The question of what came before the Big Bang transforms into what process gave rise to time itself. This leads us to one of the most radical and difficult to grasp ideas in modern physics, a concept that sounds more like science fiction than scientific theory, the holographic principle. To understand it, let's start with a paradox. In the 1970s, physicist Jacob Bekenstein made a stunning discovery about black holes. He found that the maximum amount of information, or entropy, that a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon. Think about that for a second. All the information about everything that ever fell into a black hole, every star, every planet, every book, every memory, could be entirely encoded on the two-dimensional boundary that surrounds it, not within its three-dimensional volume. It's as if the three-dimensional interior is a projection, a hologram, born from the information painted on its two-dimensional surface. The holographic principle boldly suggests that this isn't just a quirky property of black holes. It might be a fundamental feature of our entire universe. What if the three-dimensional reality we experience, the depth of space, the particles, the forces, everything, is not the fundamental reality? What if it is all a magnificent, dynamic hologram, projected from a two-dimensional surface that exists at the very boundaries of the observable universe? In this view, our cosmos is not a container of information. It is information itself, and that information is stored on a distant cosmic film. So how could this possibly relate to the universe's very first particles? To answer that, we have to venture back to the extreme conditions of the Big Bang. As we rewind time, the universe gets smaller and hotter. But in this model, it's not just the volume that's shrinking, the surface area of its boundary is shrinking too. At the moment of the Big Bang, the entire observable universe was compressed into an infinitesimally small point. Its volume was nearly zero, but its surface area was also nearly zero. The holographic principle implies that in this state, the information density on that surface was unimaginably high. The entire blueprint for our future cosmos, every galaxy, every person, every law of physics was encoded on a surface of almost zero size. As the universe began to expand, that surface area grew. The information stored there began to decode itself, to project inward and manifest as the three-dimensional reality we now inhabit. The first particles were not independent things that appeared in space. They were the first stable excitations, the first consistent pixels of this cosmic projection to lock into place. Their properties, a quark's mass and electron's charge, were not handed down from some higher law, but were determined by how information was processed and translated from the two-dimensional boundary into our three-dimensional world. The emergence of particles from the energy of the Big Bang becomes a process of translation, like a cosmic projector finally focusing to create a clear image from a blur of data. This completely transforms our understanding of the Planck epoch, that era of quantum foam we discussed earlier. That chaotic frothing of spacetime might not be the fundamental reality, but merely a blurry, low-resolution version of the projection. The true, fundamental workings of the universe are happening on that distant two-dimensional surface where time and space, as we know them, do not exist. The laws of physics that govern particles and forces in our world are, in this view, analogous to the laws of optics that govern how a hologram is displayed. They are emergent properties, not fundamental truths. The holographic principle doesn't just offer a new theory for the first particles. It suggests we've been looking at the screen all along when we should have been trying to understand the projector. Now, as we pull our focus from the grand architecture of spacetime itself, we arrive at one of the most tangible and pressing mysteries in all of cosmology, the nature of dark matter. We've mentioned it before, that invisible, mysterious substance whose gravitational pull is the hidden hand sculpting the cosmos. But what if the answer to this modern enigma is also the key to understanding the universe's very first particles? This brings us to a fascinating candidate that could have been one of the earliest inhabitants of the cosmos, the action. The story of the action doesn't begin with dark matter, but with a different, equally profound puzzle in particle physics known as the strong CP problem. Inside every proton and neutron, quarks are bound together by the strong nuclear force carried by particles called gluons. The bizarrely elegant mathematics describing this force naturally allow for a certain kind of asymmetry that would violate the combined symmetries of charge and parity. This violation should make the neutron possess a slight electric dipole moment, meaning it would have a positive end and a negative end like a tiny bar magnet. However, incredibly sensitive experiments have measured the neutron and found it to be perfectly symmetrical to an astonishing degree. Its electric dipole moment is so close to zero that it seems nature has gone out of its way to avoid this asymmetry. This is the strong CP problem. Why does the strong force seem to respect this symmetry when its own equations say it shouldn't have to? In the late 1970s, physicists Roberto Pexi and Helen Quinn proposed an elegant solution. They suggested a new, fundamental symmetry in nature that, when applied to the equations, elegantly cancels out this unwanted CP violation, explaining the neutron's perfect symmetry. Shortly after, Frank Wilczek and Steven Weinberg realized that this mechanism wouldn't just solve a math problem. it would necessarily predict the existence of a new, very light and very stable particle. Wilczek named this hypothetical particle the action after a brand of laundry detergent because it cleaned up a problem in the theory. So what does a particle invented to solve a quantum puzzle have to do with the first moments of the universe? Everything. The properties this solution demands for the action make it a perfect candidate for dark matter. It would be electrically neutral, incredibly light, potentially billions of times lighter than an electron. And most importantly, it would interact with ordinary matter only extremely weakly, barely making its presence known except through gravity. But its most crucial property for our story is that it would have been produced in absolute abundance in the hot, dense cauldron of the early universe. Theorists believe actions could not have been created in the same way as other particles. They weren't forged in collisions or decays. Instead, they are thought to have condensed out of the cooling cosmic energy field, much like water vapor condensing into frost on a cold window pane. This process, called the misalignment mechanism, likely occurred within the first few microseconds after the Big Bang. As the universe expanded and cooled through a critical temperature, a cosmic field related to the action, the Peck-Quinn field, would have settled into its lowest energy state. But in different regions of space, this settling could have happened at slightly different angles or phases. These misalignments created a kind of tension in the fabric of space, and as the universe continued to cool, this tension relaxed. The energy stored in this cosmic misalignment was released not as heat or light, but in the form of a copious, coherent vibration throughout the universe, a Bose-Einstein condensate of cold, dark actions. This means that within the first instance of time, an immense number of these exotic particles could have simply appeared, filling the cosmos with an invisible, non-interacting sea. They would have been among the very first stable particles to exist, a ghostly population born before most ordinary matter had even taken its permanent form. Their sheer numbers would have been staggering, potentially accounting for all the dark matter we infer today. And because they were produced cold and slow-moving, their gravity would have immediately begun to sculpt the cosmos. This is where the action story directly connects to the birth of the first ordinary particles. While actions themselves don't interact through the electromagnetic or strong forces, they do exert a powerful gravitational pull. In those first moments, the universe was still incredibly smooth, but it wasn't perfectly uniform. Tiny quantum fluctuations, the ones imprinted by inflation, were already there. The vast sea of actions responding only to gravity would have been irresistibly drawn to these slightly denser regions. They would have begun to clump there far earlier and far more efficiently than ordinary matter, which was still a searing, ionized plasma constantly buffeted by intense radiation pressure. These action clumps acted as gravitational seeds, creating deep, invisible wells of potential energy. Ordinary matter, the protons, neutrons, and electrons that were finally starting to form atoms, would later simply slide into these pre-existing gravitational pits. The actions, in a very real sense, built the invisible scaffolding upon which the visible universe was constructed. They provided the initial blueprint for the cosmic web of galaxies and clusters we see today. Without this early gravitational anchor provided by dark matter particles like actions, the slight overdensities in the ordinary matter might have been smoothed out by the pressure of radiation, potentially preventing the formation of galaxies and stars for much longer or even entirely. The first particles of light and matter owe their event Chinese letter, their coming together to form structure, to the silent, pervasive influence of these first dark particles, whose origins are tied to a fundamental symmetry of nature itself. Yet this ocean of possibilities, this endless cycle of rebirth, presents a profound question that has captivated thinkers for centuries. Could our universe itself have a predecessor? We've pondered the multiverse and the bounce, but what if the Big Bang wasn't a true beginning at all, but a monumental transition from a previous cosmic state that was fundamentally different from our own. This leads us to the fascinating and deeply theoretical realm of pre-Big Bang cosmology, a collection of ideas that challenge the very notion of a singular creation event. One of the most compelling visions within this framework is the ekpyrotic universe scenario, born from the mathematics of string theory and M-theory. The name ekpyrotic comes from the ancient Greek word for conflagration or out of fire, and the theory paints a breathtaking picture. Instead of an explosion from a single point, it proposes our universe began in a collision, a cataclysmic yet silent crash between two immense multidimensional membranes or branes moving through a higher dimensional space called the bulk. Imagine our entire three-dimensional universe as a vast flat sheet, one of two such sheets floating in an 11-dimensional void, slowly drawn together by an invisible force. These branes could be thought of as unimaginably large parallel worlds. As they drew nearer, their interaction would have stretched and heated our brain, filling it with an immense amount of energy in the form of quantum fields. The moment of collision, the Big Bang, was not an explosion in space, but the moment the energy of that collision was transferred into our brain, heating it to an incredible temperature and initiating the expansion we observe today. In this view, the Big Bang was the echo of a higher dimensional event, a cosmic shockwave that set our entire reality in motion. The first particles in our story were the vibrations rippling across our brain from that monumental impact, the aftershocks of a collision between worlds. What's truly remarkable about the ekpyrotic model is how it reinterprets the evidence we have. The incredible uniformity of the cosmic microwave background, which inflation explains with a period of hyper-fast stretching, is explained here by the simple fact that the two colliding branes were nearly perfectly flat and parallel. They interacted smoothly and uniformly across their entire, unimaginably vast surfaces, delivering a consistent burst of energy everywhere at once. This model also naturally produces the specific type of quantum fluctuations needed to seed galaxies, arising from the quantum mechanical jitter of the branes as they approached each other in the higher dimensional bulk. Another intriguing pre-Big Bang idea comes from string gas cosmology. This theory asks us to rewind time and imagine the universe when it was at its smallest possible size, constrained by the fundamental granularity of space suggested by string theory. In this incredibly hot, dense, and compact state, the universe wouldn't be filled with point-like particles, but with a raging gas of the fundamental strings themselves, all vibrating and interacting chaotically. This gas of strings would have been in a state of thermal equilibrium, buzzing with every possible vibrational mode. As this stringy universe began to expand, a critical threshold was crossed. According to this model, only three spatial dimensions were able to dynamically unwind and decompactify to become the large, expanding dimensions we experience today. The other dimensions remain tightly curled up, trapped by the winding modes of the strings around them. The transition from this hot, tangled, and compact state of string gas into an expanding universe with three large dimensions could have been the event we call the Big Bang. The first particles to emerge as stable entities would have been the specific vibrational patterns of the strings that were no longer constrained by the highly compact geometry, the notes that could finally ring out clearly in the new, expanding arena of our three-dimensional space. This model suggests that the dimensionality of our universe isn't an arbitrary given, but a dynamic outcome of a thermodynamic process in the early stringy epoch. These pre-Big Bang cosmologies don't just offer an alternative origin story, they fundamentally reshape the questions we can ask. They remove the intimidating barrier of the singularity, replacing a moment of infinite mystery with a physical, albeit spectacular, transition from a prior state. They open the door to a truly cyclic view of time, where universes might collide, bounce, or transition in an endless cosmic dance. The search for the first particles then expands beyond our own universe's timeline, inviting us to consider that the ingredients for everything we see may have been forged in a different cosmic era entirely, with laws and dimensions we can scarcely imagine, whose final act was to ignite the birth of our own reality. But how do we bridge the gap from that shimmering fog of quantum potential to the solid, objective reality we experience every day? This brings us to a truly fascinating theory that addresses one of the deepest puzzles in physics. How does the definite classical world emerge from the probabilistic quantum realm? This process is known as quantum Darwinism, and its role in the early universe may have been absolutely critical in selecting which of the countless quantum possibilities actually became the first stable particles. To understand this, let's revisit the famous thought experiment of Schrödinger's cat. In the bizarre rules of quantum mechanics, before we open the box, the cat is considered to be in a superposition. It is simultaneously both alive and dead. It's only when we make an observation, when we open the box and look, that this fuzzy cloud of possibilities collapses into a single, definite outcome, a purring cat or a tragic one. This has always presented a profound problem. Who or what gets to be the observer? Does it require a conscious mind? And how did the universe manage to have any definite properties before the first conscious beings evolved to look at it? Quantum Darwinism offers a powerful and elegant solution. It proposes that the observer isn't a person at all, it's the environment. Imagine that cat in its box is constantly interacting with its surroundings. Air molecules are bouncing off it, photons of light are hitting it, even the subtle force of gravity is acting upon it. Each of these tiny interactions is like a miniature, spontaneous measurement. Information about the cat's state, whether it's alive or dead, is constantly being copied and broadcast out into the environment. This information is replicated thousands, millions, even trillions of times, spreading through the air in the box like a rumor that can't be contained. Now, when you come along to open the box, you don't cause the collapse. Instead, you simply intercept a small fraction of that already broadcast information. You learn the outcome that the environment has already redundantly encoded and agreed upon. The superposition hasn't been destroyed. Its information has been copied so many times that it has effectively become a stable, objective fact. In this view, the classical world isn't fundamental. It's what emerges through this process of environmental monitoring and information proliferation. The properties we consider objective are simply the quantum states that are the most robust, the ones that can withstand this constant interaction and be copied the most efficiently. They are the ones that survive a process of natural selection, hence the name quantum Darwinism. Now, let's project this incredible idea back to the universe's first moments. Picture the Planck epoch or the immediate aftermath of the Big Bang. The cosmos was a seething ocean of quantum foam, a realm where every possible field configuration, every potential particle state, existed in a blur of superpositions. There was no environment in the classical sense. Everything was interacting with everything else in a chaotic quantum dance. But as the universe expanded and cooled, it began to differentiate. The first field started to condense, and space itself became a medium. This is where quantum Darwinism began its work. The countless quantum fluctuations, those tiny seeds that would later become galaxies, were all vying for existence. But which ones would become real? Which possibilities would be selected to become the actual particles with definite mass, charge, and spin that would go on to build our world? The theory suggests it was the ones that most effectively imprinted their information on the emerging environment. A particular vibrational mode in the Higgs field, for instance, that could consistently interact with other nascent fields would have its state copied and reinforced. It would leave its mark on the inflaton field, on the gravitational field, on the very fabric of spacetime as it expanded. This redundancy of information would make that particular state objective. It would transition from a mere quantum possibility to a classical fact, a building block with fixed properties. This process wouldn't have been random. Just like in biological evolution, the quantum states that were most fit were those that were the most stable and that could form the most consistent correlations with their surroundings. This environmental selection pressure could explain why we have the specific particles we do. The electron, with its specific mass and charge, may not be unique. It might simply be the quantum state that was most successful at getting itself copied and broadcast throughout the early universe. Its properties became objective because they were the most communicable, the most imprinted upon the cosmic environment. In this way, the solidity of the particles that make up our bodies isn't an illusion, but it is a relational property. It's a testament to their ability to consistently interact with the world and thereby define it. Quantum Darwinism provides a mechanism for how the universe observed itself into existence long before any eye was there to see it. But this entire cosmic journey through bounces and brains, quantum foam and vibrating strings leads us to a staggering and deeply controversial question that sits at the intersection of physics and philosophy. What if the reason we find ourselves in a universe with such perfectly tuned particles and forces is simply because we are here to observe it? This is the essence of the anthropic principle, an idea that suggests the fundamental constants we measure are not arbitrary, but are necessarily constrained by the fact that conscious life exists to measure them. To grasp the sheer improbability of our universe's recipe, consider the precise values that had to be set in stone for particles to form atoms, stars, and eventually us. The strength of the strong nuclear force which binds atomic nuclei together is tuned with incredible precision. If it were just a few % stronger, protons would pair up into diprotons and hydrogen would fuse into helium almost instantly in the early universe, burning up all the fuel for stars before life could ever emerge. If it was slightly weaker, no elements heavier than hydrogen would be stable at all, and the periodic table would be a single, lonely entry. The mass of the electron is another exquisitely fine-tuned parameter. If it were much different, the chemical bonds that form molecules would be impossible, rendering the complex chemistry of life stillborn. Even the cosmological constant, which drives the accelerating expansion of the universe, is fine-tuned to an accuracy of 1 part in 10 to the power of 120, a number so incomprehensibly small that it defies any notion of random chance. Faced with this overwhelming evidence for fine-tuning, physicists have proposed two main versions of the anthropic principle. The weak anthropic principle is a relatively straightforward selection effect. It states that we must find ourselves in a universe capable of supporting life because we couldn't possibly exist in one that doesn't. It doesn't say the universe was designed for life. It just acknowledges that our very existence as observers filters the kind of universe we can perceive. We are, in a sense, cosmic lottery winners who only hear about the winning tickets. The strong anthropic principle, however, takes a much more profound and controversial leap. It suggests that the universe must in some way have properties that allow life to develop within it at some stage in its history. This version implies a deeper law or mechanism that compels the constants of nature to fall within the life-permitting range. For the origin of the first particles, the anthropic principle offers a startlingly different perspective. It suggests that the properties of those particles, the specific mass of the quark, the charge of the electron, the strength of their interactions, were not determined by a unique fundamental law. Instead, they are merely one possible combination that, purely by chance, fell within the narrow window that allows for complexity. In this view, the first particles weren't special, they were just lucky. Their characteristics were not forged by necessity but selected by the eventual consequence of their own existence. The quantum fluctuations that gave them birth did not have a predetermined outcome. They simply produced a vast array of possibilities, and we find ourselves in the one slice of reality where the dice roll produced a habitable world. This line of thinking finds its most powerful expression when combined with the concept of the multiverse. If eternal inflation or string theory's landscape is correct, and there are indeed an infinite number of universes, each with randomly different physical constants and laws. Then the anthropic principle shifts from being a philosophical curiosity to a practical, predictive tool. In an infinite multiverse, every possible combination of constants will be realized somewhere. The vast, overwhelming majority of these universes will be stillborn cosmic deserts where particles instantly decay, or featureless soups where no structure ever forms, or collapsing voids that flash out of existence in an instant. But in an infinitesimally small fraction of these universes, the random dials will land on the perfect settings for atoms, chemistry, and life. We inevitably find ourselves in one of those rare, habitable bubbles, not because it was designed for us, but because we are a product of its conditions. The first particles in our history had the right properties because in the cosmic casino, our universe happened to hit the jackpot. While the story so far has focused on the particles that build atoms and respond to light, there's an entire ghostly population that has been streaming through the cosmos since its very first second, subtly shaping everything from the largest structures to the smallest nuclear reactions. These are neutrinos, and despite being among the most elusive entities in the universe, their influence on cosmic history is profound and undeniable. To understand their role, we first need to grasp what makes them so strange. Neutrinos are elementary particles like electrons, but with a crucial difference: they have no electric charge and are almost completely massless. This means they barely interact with anything at all. Trillions of them are passing through your body every second from the sun and other cosmic sources without a single one noticing you're there. This ghostly nature made them incredibly difficult to detect and even harder to understand. For a long time, the standard model of particle physics assumed they had exactly zero mass. But groundbreaking experiments at the end of the 20th century revealed something astonishing. Neutrinos do have mass, but it is vanishingly small. An electron neutrino, for instance, has a mass at least 6 million times smaller than that of an electron. This tiny but non-zero mass is a monumental discovery because it's the first clear crack in the otherwise robust standard model, pointing directly toward new, undiscovered physics. But more importantly for our story, it means that in the unimaginable energy of the Big Bang, neutrinos were produced in absolutely staggering numbers, second only to photons of light themselves. To appreciate their impact, we need to journey back to just 1 second after the Big Bang. At this point, the universe had cooled to a temperature of about 10 billion degrees, a furnace still hot enough to keep most matter dissolved into a plasma of quarks and electrons. But it was also the moment neutrinos decoupled from the rest of the cosmic soup. Because they interact so weakly, they were the first particles to essentially stop talking to everyone else. They flew free, creating a pervasive, invisible background sea that still permeates all of space today. A cosmic neutrino background analogous to the cosmic microwave background of light that came later. This moment of decoupling was a critical handoff. The energy these neutrinos carried away with them directly influenced the rate at which the universe cooled, setting the precise stage for the next major act, the formation of the first atomic nuclei. This brings us to their first major cosmological role, a Big Bang nucleosynthesis, the process that forged the universe's first hydrogen and helium. This happened between 1 second and a few minutes after the Big Bang. The entire future fuel supply for every star was determined in these first few minutes. The number of neutrinos present, and more specifically their interaction rates, played a crucial part in this delicate nuclear ballet. The weak nuclear force, which governs processes like nuclear decay, is also responsible for interactions that change a proton into a neutron and vice versa. Neutrinos are key players in these reactions. The density and energy of the cosmic neutrino background directly influence the equilibrium between protons and neutrons. Since a helium nucleus requires 2 protons and 2 neutrons, the final ratio of these particles decided how much of the early universe became hydrogen versus helium. Even a slight change in the number of neutrino types or their properties would have drastically altered this outcome. If there were more types of neutrinos, for example, the expansion rate of the universe during this critical window would have been faster, changing the proton-to-neutron ratio and resulting in a universe with vastly different amounts of primordial helium. The fact that our observed helium abundance matches predictions so precisely is a powerful confirmation that we have the correct number of light neutrino species 3 and that their behavior is well understood. In this way, the success of nucleosynthesis is a silent testament to the neutrino's subtle but essential presence at the dawn of time. But neutrinos weren't done shaping the cosmos after those first few minutes. Their most lasting influence may be on the very architecture of the universe itself, the cosmic web of galaxies and clusters. This is where their tiny mass becomes cosmologically enormous. Despite each individual neutrino being almost impossibly light, their sheer numbers are so vast that collectively, they should make up a significant portion of the universe's total mass, contributing to the overall budget of dark matter. For decades, they were a leading candidate to be the dark matter. While we now know they are too fast-moving and light to be the primary component, they still play a fascinating and unique role in structure formation. The key is their speed. In the early universe, neutrinos were born moving at almost the speed of light. This makes them what cosmologists call hot dark matter. Fast-moving particles like this have a powerful smoothing effect. Their high velocity allows them to stream freely out of small, emerging gravitational wells, effectively washing out any nascent structures that are too small. Think of it like trying to build a sandcastle with dry, fine sand. The grains just slip away. Neutrinos would have suppressed the formation of the smallest dwarf galaxies and altered the entire hierarchy of how galaxies clump together. The fact that we see a universe filled with both immense clusters and tiny dwarf galaxies tells us that the dominant form of dark matter must be cold or slow-moving. However, the precise way in which the largest structures formed, the exact number and distribution of the biggest galaxy clusters, is exquisitely sensitive to the total mass of the neutrinos. By mapping the cosmos on the grandest scales, we are essentially weighing the neutrino. This makes cosmology a powerful neutrino hunting ground. Particle physics experiments on Earth can tell us that neutrinos have mass, but they struggle to measure the absolute lowest possible value of that mass. The cosmos itself provides the scale. The gravitational influence of the cosmic neutrino background, subtlety imprinted on the distribution of galaxies, and the faint ripples in the cosmic microwave background gives us our best constraints. Current observations tell us that the combined mass of the three neutrino types must be incredibly small, less than 1/10 of an electron volt. To put that in human terms, that's at least 1 billion times less than the mass of a single proton. This minuscule mass is the biggest clue that neutrinos are our window into physics beyond the standard model. The mechanism that gives them mass is almost certainly different from the Higgs mechanism that gives mass to quarks and electrons. Many theorists believe neutrino mass could arise from a seesaw mechanism, involving incredibly heavy, sterile neutrino partners that we have yet to discover. Others propose they are Majorana particles, meaning that a neutrino is its own antiparticle, a property that could help explain the matter-antimatter asymmetry of the universe. The fact that they oscillate spontaneously, changing from one type to another as they travel, is direct proof of their mass and a phenomenon that has no analogy in any other particle. Every neutrino that reaches us from the Sun or a distant supernova carries encrypted information about its origin and its journey, a message written in the language of its oscillations. So, while they may be the ghosts of the particle world, neutrinos are anything but insignificant. They were there at the beginning, cooling the universe and setting the table for the first elements. They helped write the blueprints for the cosmic web, their tiny masses acting as a fine-tuning dial on the largest structures we can observe, and they continue to challenge our understanding of fundamental physics, their mysterious masses hinting at a grander, more complete theory of nature waiting to be discovered. They are a perfect reminder that in the cosmos, the most silent participants often have the most powerful stories to tell. But to understand why the absence of something could be so profoundly important, we need to journey to a moment of unimaginable unity in the early cosmos. This brings us to the Grand Unification epoch, a fleeting sliver of time before even the first full second had passed. In this era, the universe was so incredibly hot and dense that the three fundamental non-gravitational forces, the electromagnetic force, the weak nuclear force, and the strong nuclear force, are theorized to have been merged into a single, majestic superforce. This is the realm of grand unified theories, or GUT, which attempt to describe this incredible symmetry. In this unified state, the distinctions between a quark and an electron would have been meaningless. They were all just different manifestations of a single underlying field. And it is from this perfect, symmetrical state that one of the most tantalizing predictions in all of physics emerges: the magnetic monopole. We are all familiar with magnets. Every child knows that a bar magnet always has two poles, a north and a south. If you break that magnet in half, you don't get an isolated north and an isolated south. You get two new, smaller magnets, each with its own pair of poles. This seems to be an unbreakable rule of our universe. Magnetic poles always come in pairs. They are always dipoles, but grand unified theories, in their breathtaking mathematical elegance, demand that this was not always the case. They predict that as the universe cooled and this perfect GUT symmetry was broken, it wouldn't have transitioned smoothly. Instead, it would have formed defects in the fabric of spacetime itself, much like cracks forming in ice as water freezes. And one type of these topological defects would be a particle that carries a single, isolated magnetic charge, a north pole without a south, or a south without a north. A magnetic monopole. These wouldn't be ordinary particles. A magnetic monopole would be an astoundingly heavy object, perhaps as massive as a bacterium, which is gargantuan by particle standards. It would possess a magnetic charge so powerful that it could literally rewrite the rules of quantum physics as we know them. And according to the simplest applications of grand unified theories, these monstrous particles should have been produced in absolutely staggering numbers during that phase transition, frozen into the fabric of the expanding universe as permanent relics of its hotter, unified past. The math suggested they should be as common as protons, meaning there should be at least one in every cubic centimeter of the universe. Our planet, our solar system, even our galaxy should be utterly saturated with them. You should be able to find one in a handful of moon dust or detect one with a relatively simple experiment. Yet, despite decades of meticulous searching with some of the most sensitive detectors ever built, from ancient mica crystals to vast loops of superconducting wire, not a single definitive magnetic monopole has ever been found. Their absence is a deafening silence in physics, a glaring contradiction known as the monopole problem. This isn't just a minor puzzle, it was a full-blown crisis for cosmology in the late 1970s. The majestic edifice of grand unification, which so beautifully explained the unification of forces, also seemed to predict a universe that looks nothing like our own, a universe cluttered with enough heavy magnetic relics to dramatically alter the evolution of galaxies and potentially even prevent life from forming. The theory was too successful for its own good, predicting particles that simply weren't there. This profound discrepancy between an elegant theory and an inconvenient reality is precisely what led physicists to seek a radical solution. The most compelling answer arrived in the form of cosmic inflation. As we discussed earlier, Alan Guthr's theory of a period of hyper-fast exponential expansion wasn't just invented to solve the flatness and horizon problems. The monopole problem was a primary motivator. Inflation provides the perfect cosmic broom. Imagine those monopoles were produced in abundance as the theories said they must have been. Then inflation kicked in. That brief period of incredible stretching would have diluted their density to virtually zero. The entire observable universe, which inflated from a tiny, microscopic patch, would likely contain only a handful of these relics, if any at all. The monopoles are still out there in principle, but they have been swept so far beyond our cosmological horizon that they are effectively gone from our reality. In this way, the stunning absence of magnetic monopoles became one of the strongest pieces of indirect evidence that a period of inflation must have actually occurred. The nothingness we observe is a powerful clue to the everything that once was. The story of the magnetic monopole is a perfect example of how a negative result in science can be more powerful than a discovery. Their non-detection forced us to invent a better, more complete theory of the universe's infancy. It reshaped our understanding of how symmetries break and how the first particles condensed out of the cooling cosmic energy. It tells us that the transition from a unified state to the complex world of separate forces was likely not a simple, quiet cooling, but a dramatic inflationary event that fundamentally reset the density of the cosmos. So while we may never hold a magnetic monopole in our hand, its ghost continues to guide our theories, a permanent monument to a unified past we can only infer from the profound emptiness it left behind. But this elegant story of the Higgs field as the sole source of mass while triumphant is not the only idea on the table. What if the Higgs boson we discovered isn't a fundamental particle at all, but a composite object, a kind of mirage emerging from a deeper, more complex reality? This is the intriguing premise of Technicolor theories, which propose that the mechanism giving particles their mass might be far more dynamic and powerful than a single, pervasive field. To understand this alternative, we need to look not to the immense scales of cosmology, but to the intricate world of condensed matter physics here on Earth, specifically to the phenomenon of superconductivity. Inside a superconductor, electrons pair up and move with zero resistance, and in doing so, they exclude magnetic fields in a famous effect known as the Meissner effect. The British physicist Philip Anderson realized that this expulsion of magnetic fields looks mathematically exactly like a particle gaining mass. Within the superconductor, the photon, the normally massless carrier of light, effectively behaves as if it has become heavy. This isn't because of a fundamental Higgs field, but because the photon is interacting with the collective, paired-up state of all the electrons. The mass is emergent. It's a collective phenomenon born from the interactions of more fundamental constituents. Technicolor theories take this brilliant insight and scale it up to a cosmic level, suggesting that the entire universe could be one giant, natural superconductor for a new, hidden set of forces. In this vision, the Higgs field is not elementary. Instead, it's a composite particle bound together by a new, ultra-strong force, the Technicolor force, which operates at energies far higher than those we currently probe. This force would be mediated by a new set of particles, analogous to the gluons of the strong nuclear force, but even more powerful. Just as the strong force binds quarks together to form protons and neutrons, the Technicolor force would bind together hypothetical technifermions to form composite particles, including one that looks and acts just like the Higgs boson. The mass-generating mechanism wouldn't be a gentle, omnipresent field permeating the vacuum, but a fierce, binding force that literally forges mass through the intense interactions of these more fundamental techni-particles. This completely rewrites the narrative of the early universe. Moments after the Big Bang, the cosmos would have been filled with a seething plasma of these technifermions, buzzing with the energy of the Technicolor force. As the universe expanded and cooled past a critical temperature, this hot soup would have undergone a dramatic phase transition, much like water freezing into ice. The technifermions would have condensed into a paired state, a cosmic superconductor. It is this condensation, this collective pairing, that would have spontaneously broken the electroweak symmetry, endowing the W and Z bosons with mass and giving quarks and electrons their specific properties. The Higgs mechanism, in this view, is the aftermath, the visible signature of this much deeper and more violent cosmic process. The appeal of such a theory is its naturalness. It doesn't rely on a single, seemingly fine-tuned elementary particle to do all the work. It uses known physics, the dynamics of strong forces and phase transitions, and applies it to the highest energy problem we have. For a time, Technicolor was a leading contender to explain mass without the Higgs. However, the model, in its simplest form, ran into significant problems. It predicted a host of other composite particles that should have been visible at particle colliders, and it struggled to generate the large mass difference between the top quark and other particles, a feature we now observe. The discovery of a Higgs boson with properties that so neatly match the predictions of the standard model was a major blow to the simplest Technicolor ideas. Yet the core concept is so compelling that it has evolved. Modern, walking Technicolor or composite Higgs models incorporate elements of this thinking, suggesting the Higgs could be a composite particle but one that is unusually light, or pseudo-Nambu-Goldstone boson, which allows it to mimic a fundamental particle at the energies we can currently access. These models remain active areas of research, especially as we seek to understand what lies beyond the standard model. They remind us that the story of the first particles may not be a simple one of fields and sparks, but one of cosmic forces forging reality in a hidden Technicolor furnace, a process whose full majesty we have only just begun to glimpse. But to truly grasp how these vibrations could give rise to the first particles with such specific properties, we must venture beyond the familiar confines of our three-dimensional world into a realm that sounds like pure science fiction, the possibility of extraspatial dimensions. This isn't a new idea. It dates back to the early 20th century with the work of mathematician Theodore Kaluza. He made a stunning discovery. By simply rewriting Einstein's equations of general relativity in 5 dimensions, 4 of space and 1 of time, he found that the equations for gravity naturally produced a second set of equations that perfectly described James Clerk Maxwell's theory of electromagnetism. It was as if the force of light was an inevitable geometric consequence of a higher dimensional reality. This was a breathtaking unification, suggesting that the fundamental forces might not be separate entities at all, but merely different facets of the geometry of a higher dimensional space. Of course, an immediate question arises: if there are extra dimensions, where are they? Why don't we see them or move through them? This is where the idea of compactification comes in, an idea later refined by Oscar Klein. Imagine a long, thin garden hose stretched across a field. From a distance, it looks like a one-dimensional line, but if an ant were to crawl onto that hose, it would discover a second, tiny, circular dimension curled around the hose's circumference. Our universe could be like that. The 3 dimensions of length, width, and height are vast and expanding, but there could be additional spatial dimensions that are curled up or compactified on an astonishingly small scale at the so-called Planck length. This scale is so minuscule that a billionth of a billionth of a billionth of a meter wouldn't even come close to describing it. It's a realm far beyond the reach of our most powerful microscopes, but potentially accessible through the behavior of the universe's very first particles. This geometry has a direct and profound impact on how a vibrating string manifests itself in our 3-dimensional world. A string isn't confined to just vibrating in our 3 large dimensions. It can also vibrate in these tiny, compactified ones, but because these extra dimensions are so incredibly small, they force the string's vibrations to adopt only very specific, quantized frequencies, much like how the air in a flute can only resonate at certain notes determined by the length of its tube. Each of these allowed vibrational notes corresponds to a different particle with a specific mass and charge as observed in our 3-dimensional universe. A single type of fundamental string vibrating in a higher dimensional space can therefore produce an entire family of different particles. These higher dimensional resonances are what physicists call Kaluza-Klein particles. In the searing heat of the very early universe, when energies were high enough to probe these tiny scales, these Kaluza-Klein states would have been incredibly significant. The first particles might not have been the lightweight electrons and quarks we know today, but their much heavier, higher dimensional counterparts. Imagine a string vibrating with immense energy, not just back and forth, but also in tight, complex loops within these curled-up dimensions. This energetic vibration would manifest as a particle with a tremendous mass, a relic from when the full symmetry of the higher dimensional space was apparent. As the universe expanded and cooled, these heavy Kaluza-Klein particles would have decayed away, transforming into the lighter, stable particles that now form the bedrock of our material world. Their existence, even if fleeting, could have played a crucial role in processes like baryogenesis, helping to create the matter-antimatter imbalance that allowed our universe to exist. The specific way these extra dimensions are folded and curled, their exact geometric shape effectively writes the laws of physics for our low-energy, three-dimensional reality. This concept is known as the string theory landscape. The geometry determines the allowed vibrational frequencies, which in turn set the masses of particles, the strengths of the fundamental forces, and even the number of generations of matter. A slight change in the geometry, a different way of curling up these dimensions, would result in a completely different universe with different physical constants, perhaps one where atoms could never form or where gravity was too weak to hold galaxies together. In this view, the properties of the first particles were not arbitrary. They were a direct and unavoidable consequence of the hidden topological architecture of the cosmos, a six-dimensional shape whose contours we are still trying to discern from the faint vibrational echoes of the Big Bang. But if the holographic principle suggests our reality is a projection, and quantum Darwinism explains how it became objective, could the projector itself be something as terrifyingly real as a black hole? This leads us to one of the most mind-bending and speculative ideas in all of cosmology, the theory that our entire universe might be the interior of a black hole formed in a parent cosmos. At first glance, this sounds like the stuff of fantasy, but it emerges from a desperate struggle to solve one of physics' most vexing problems, the black hole information paradox. To understand this, we need to dive into the paradox itself. As we discussed, when something falls into a black hole, it vanishes behind the event horizon, seemingly lost forever. But Stephen Hawking's work on quantum mechanics showed that black holes aren't completely black. They slowly evaporate over astronomical timescales by emitting what we now call Hawking radiation. This radiation, however, appears to be purely thermal, a featureless glow that carries no information about what fell in. It's like burning a library. The heat and smoke that rise from the ashes tell you nothing about the specific books that were consumed. When the black hole finally evaporates completely, all the information about the stars, planets, and particles that ever fell into it would be permanently erased from reality. This violates a fundamental tenet of quantum mechanics. That information cannot be destroyed. It must always be preserved in principle, even if scrambled beyond recognition. This is the information paradox, a direct conflict between general relativity and quantum theory that has puzzled physicists for decades. Now, one radical solution to this paradox is to suggest that the information isn't lost at all. What if, instead of being destroyed, the information of everything that falls into a black hole is not stored on its surface, but is used to create an entirely new reality inside it? This is the heart of black hole cosmology, the mathematics of a collapsing star forming a black hole, when viewed from the perspective of an observer falling in, doesn't necessarily end at a point of infinite density. Under certain solutions to Einstein's equations, the interior of a black hole can be described as a rapidly expanding universe. From the outside, the black hole is a tiny, incredibly dense object. But from the inside, space is stretching at a ferocious rate. The event horizon isn't a wall of fire, it's a cosmic horizon, much like our own cosmological horizon, marking the limit of what we can see. In this view, our Big Bang might have been the violent birth of a black hole in a larger parent universe. This idea provides a stunningly elegant, albeit speculative, answer to the question of our universe's first particles and its finely tuned laws. When a star collapses in the parent universe, it does so under a specific set of physical constants. The energy, mass, and angular momentum of that collapsing star would determine the initial conditions of the new universe blossoming within. The resulting expansion inside the black hole, our Big Bang, would inherit its properties from the parent. The specific way the parent universe's laws of physics govern that collapse could directly seed the fundamental constants we observe. The mass of the electron, the strength of the forces, the number of dimensions, these might not be arbitrary, but could be a natural consequence of the specific formation process of our particular black hole. In a sense, the first particles in our cosmos were forged in the gravitational fire of a dying star in another reality, their properties imprinted by the physics of a world we can never see. This also offers a potential and deeply poetic mechanism for a cosmic evolutionary cycle. Universes that give birth to many black holes would, in turn, create many offspring universes inside them. Those offspring would inherit their physical laws, perhaps with slight random variations due to quantum fluctuations during the collapse. Universes with constants that allow for prolific star formation and black hole creation would be more fertile, producing more offspring that carry their successful genetic code of physical laws. Over countless generations, this could lead to a form of natural selection favoring universes like our own that are stable, long-lived, and capable of creating black holes. We wouldn't need a multiverse of infinite possibilities. We would have a growing family tree of cosmoses, each born from a singularity in its parent, with the first particles of each new generation carrying the legacy of its ancestry. This idea transforms the cosmos from a static arena into a living, breathing, and reproducing entity, where the laws of physics themselves are not fixed but evolve across generations. But for all the grandeur of black holes birthing new universes, what if the very fabric of space and time they're made of is not the smooth, continuous canvas we've always imagined? This leads us to a theory that is perhaps the most radical reimagining of reality's foundation, the idea of causal sets. At its heart, this theory proposes a profoundly simple yet alien concept. Space and time are not fundamental. They are not a stage, they are not a smooth, malleable fabric. Instead, they are emergent properties that arise from something far more basic, a vast, chaotic cloud of discrete, individual events, connected only by a single, fundamental relation, which event caused which other event. To grasp this, try to forget everything you know about a continuous reality. Our everyday experience tells us that space is infinitely divisible. You can always cut a distance in half, and then in half again forever. Time seems to flow like a river, but causal set theory suggests this is a grand illusion, a mirage created by the sheer number of these fundamental building blocks. Imagine reality is not a movie but a flipbook. A movie gives the illusion of continuous motion, but it's actually made of individual static frames. If you flip through the pages fast enough, your brain blends them into a seamless story. Now, imagine the universe is that flipbook. Each page is a single, fundamental atom of space-time, a point-like event with no size, no duration, and no structure whatsoever. The only thing these atoms possess is a relation to other atoms, a basic before and after, a cause and effect. This web of causal relationships is the only fundamental thing that exists. The stunning implication is that the smooth, four-dimensional spacetime of Einstein's relativity, with its warping masses and bending light, is not the starting point. It is a large-scale approximation, a statistical average that emerges from the collective behavior of this enormous number of discrete causal elements. The geometry of the universe, the very distance between stars and the flow of time itself, is a consequence of the pattern of connections in this underlying causal set. This means that in the very first moments of the universe, there was no space and there was no time as we know them. There was only a sparse, rapidly growing network of these causal events, each new event linking to previous ones. The Big Bang, in this view, is not an explosion in space and time, but the very beginning of this network's growth, the first cause that would eventually lead to an astronomical number of effects. So how do particles, with their specific properties like mass and spin, emerge from this abstract web of causality? The theory suggests that particles are not fundamental things that move through this network. Instead, they are persistent, stable patterns within the network itself, specific, resonant structures of causal connection that propagate through the set. Think of it like a soliton, a stable wave that can travel through a medium without losing its shape, like a tsunami wave crossing an ocean. An electron, in this view, might be a self-sustaining pattern of causality, a specific way that new events are consistently linked to previous ones in a way that preserves certain properties. Its mass could be related to how tightly clustered its causal links are, while its motion would be this pattern propagating through the growing set of events. The first particles, then, were not born into a universe of space and time. They were the first stable, self-reinforcing patterns to crystallize out of the chaotic, early growth of the causal set itself, their familiar properties mere shadows of a deeper causal architecture. But for all the grand theories about what those first particles were and how they came to be, there is one number that stands as perhaps the single most embarrassing and profound puzzle in all of modern physics. A number so inexplicably fine-tuned that it has been called the worst prediction in the history of science. This is the cosmological constant problem, and it strikes at the very heart of our understanding of the vacuum of space itself and the energy that must have filled it at the dawn of time. To understand the sheer scale of this problem, we need to start with what we think we know. Quantum field theory tells us that what we perceive as empty space is anything but empty. It's a seething, bubbling foam of virtual particles, pairs of particles and antiparticles constantly flickering in and out of existence, borrowing energy from the vacuum for an impossibly brief moment. This isn't just theoretical. We can measure the effects of this quantum jitter in experiments like the Casimir effect, where two metal plates placed incredibly close together in a vacuum feel a slight push because the quantum fluctuations between the plates are restricted compared to the boundless fluctuations outside. This proves that the vacuum has a real, measurable energy density. We can even calculate what this energy density should be by summing up all the possible contributions from every known quantum field and every possible vibrational mode, all the way down to the Planck scale. And this is where the math goes completely off the rails. When physicists perform this calculation, the result is a number of such staggering magnitude that it defies comprehension. The predicted vacuum energy density is around 120 orders of magnitude. That's a 1 followed by 120 zeros, larger than the value we actually observe from cosmological measurements. To put that incomprehensible error into perspective, it's the difference between the energy stored in a single drop of water and the energy contained within the entire observable universe. It's a discrepancy so vast that if our theoretical prediction were correct, the incredible repulsive force generated by this vacuum energy would have ripped every single atom in the universe apart within a fraction of a second after the Big Bang, preventing any structure, from galaxies to molecules, from ever forming. Clearly, that didn't happen. So why is the observed value of dark energy, which drives the universe's accelerated expansion, so incredibly small yet not quite zero? This isn't just a minor accounting error. It's a screaming contradiction that suggests something is fundamentally wrong with our theories. particularly where they meet at the intersection of quantum mechanics and general relativity. The cosmological constant, represented by the Greek letter lambda in Einstein's equations, is the term that describes this energy inherent to the fabric of space itself. The problem is that our two most successful theories are giving us two completely different answers for what lambda should be. Quantum mechanics says it should be enormous. General relativity, when combined with our observations of the expanding universe, says it must be almost immeasurably tiny. This chasm between prediction and observation is the cosmological constant problem, and solving it may require a revolution in physics as profound as the ones that gave us quantum theory and relativity in the first place. So how could this monumental fine-tuning possibly relate to the universe's first particles? The connection lies in the very nature of those primordial quantum fields. The vacuum energy we calculate today is a sum of all the contributions from every quantum field that has ever existed. This means its value was set in the earliest moments of the universe, when those first fields were condensing out of the Planck epoch froth. The properties of those fields, their symmetries, their coupling constants, their very existence determined the initial setting for the vacuum energy. Perhaps there was a mechanism in that first fleeting instant that dynamically drove the cosmological constant to a value very near zero. Some theories propose a form of spontaneous symmetry breaking, similar to the Higgs mechanism but acting on the vacuum itself, that cancelled out the enormous positive energy with an equally enormous negative energy, leaving behind only the tiny residual value we see today. It's as if the universe performed a perfect cosmic balancing act at its birth, leaving behind only the faintest change. This idea of a cancellation leads to one of the most controversial potential solutions, the anthropic principle. If the value of the cosmological constant is not determined by a unique, fundamental law, but can vary from one universe to another in a vast multiverse, then its value in our universe isn't a puzzle to be solved, but a selection effect to be acknowledged. In the overwhelming majority of universes, lambda is far too large, and those universes expand too violently for stars or galaxies to ever form. In another large fraction, it might be negative, causing the universe to recollapse into a big crunch almost immediately. We, of course, find ourselves in one of the rare habitable universes where the value is almost zero, allowing for billions of years of peaceful expansion and the evolution of life. From this perspective, the cosmological constant isn't fine-tuned for life. Life is a product of its rare habitable value. The first particles emerged in a universe whose vacuum energy was, by sheer chance, compatible with their eventual assembly into complex structures. Yet many physicists find this explanation deeply unsatisfying, as it seemingly abandons the search for a dynamical, predictive reason. This has spurred other, more mechanical theories. One fascinating proposal involves a new, ultra-light particle that couples to the vacuum energy. As the universe expands, this field evolves and its value shifts, acting as a sort of automatic dial that adjusts the cosmological constant, keeping it near zero for most of cosmic history. Another, even more radical idea from string theory is the concept of the landscape, where the different ways of curling up the extra dimensions give rise to a stupefyingly large number of possible vacuum states, perhaps 10 to the 500 different ones, each with its own value for the constants of nature, including lambda. In this vast landscape, a universe with our specific tiny value, while incredibly rare, is statistically inevitable. The cosmological constant problem is more than just a theoretical curiosity. It is a direct portal into the deepest laws of nature. It tells us that our understanding of nothing, the pure, empty vacuum, is still profoundly incomplete. The resolution to this problem will likely force us to rethink the very nature of those first quantum fields, the symmetry principles that govern them, and perhaps even the number of dimensions in which they vibrated. It stands as a silent monument to our ignorance, a reminder that for all we have learned about the universe's first particles, the energy of the void from which they sprang remains one of its most enduring and humbling mysteries. Yet for all the radical ideas we've explored, from vibrating strings to emergent spacetime, they all share a common, silent assumption that the stage upon which particles dance is a smooth, continuous manifold, a geometric canvas that can be divided infinitely. But what if this most basic assumption is wrong? What if the geometry of spacetime itself is fundamentally different at the deepest level, governed by a kind of algebra that makes our classical notions of points and distances obsolete? This brings us to a profoundly abstract yet beautiful framework known as non-commutative geometry, a theory that suggests the coordinates of spacetime might not commute at the most fundamental scales. To understand what non-commutative means, we need to take a quick detour into the quantum world. In our everyday experience, the order in which you do things doesn't usually matter. If you drive 5 miles north and then 3 miles east, you end up in the exact same spot as if you drive 3 miles east and then 5 miles north. The operations of moving north and east commute, their order is interchangeable, but in the quantum realm, this is famously not the case for properties like position and momentum. Measuring a particle's position first and then its momentum will give you a different outcome than measuring its momentum first and then its position. The operators for these quantities do not commute, and this fundamental non-commutativity is the very source of Heisenberg's uncertainty principle, the bedrock of quantum mechanics. Now, non-commutative geometry proposes a breathtaking extension of this principle. What if the very coordinates of spacetime themselves behave like quantum operators? What if telling someone the location of an event requires not just 3 spatial numbers and 1 time number, but an inherent uncertainty because those numbers refuse to commute? In this vision, the concepts of here and there become fuzzy at scales around the Planck length. It would be impossible to pinpoint an event to a specific, infinitesimal point because the very act of measurement would disturb the spacetime fabric itself. The universe at its core would possess a fundamental graininess, not because it's made of discrete blocks, but because its geometric coordinates are inherently uncertain, much like the properties of a quantum particle. This isn't just a philosophical shift, it's a mathematical revolution that redefines what geometry is. In traditional geometry, as laid out by Euclid and later generalized by Einstein, a space is described by its points and the distances between them. But if points lose their precise meaning at the quantum level, we need a new language. Non-commutative geometry, pioneered by mathematicians like Elaine Kahns, provides this language. It describes reality not in terms of points, but in terms of algebras, the rules governing how mathematical objects combine. In this framework, the smooth, continuous space of general relativity emerges as a large-scale approximation from a more fundamental, non-commutative algebraic structure, much like the smooth flow of water emerges from the chaotic jostling of individual molecules. So how could this abstract mathematical principle have given rise to the universe's first particles and forces? The theory suggests that in the extreme conditions of the early universe, this non-commutative nature of spacetime would have been dominant. The violent fluctuations and fuzziness would have meant that particles couldn't be thought of as distinct objects moving through space. Instead, both particles and the forces between them would have been excitations or manifestations of the spacetime geometry itself. The different vibrational modes allowed by the non-commutative algebra could directly correspond to different types of particles. An electron might be one specific type of excitation, while a photon is another. In this view, the standard model of particle physics, with its zoo of particles and forces, isn't a separate theory from gravity. It is the intricate particle spectrum that emerges from the particular non-commutative geometry of our universe. This approach offers a stunningly unified picture. The forces we experience, electromagnetism, the weak and strong nuclear forces, are not fundamental in the same way. They are gravitational forces in a higher dimensional non-commutative space that, when viewed from our four-dimensional perspective, appear as the diverse interactions of the Standard Model. The Higgs mechanism itself, which gives particles mass, could find a natural explanation as a geometric phenomenon within this framework, a consequence of the way the non-commutative algebra breaks symmetry as the universe cools. The first particles, then, were not things that appeared in the universe. They were the universe's geometry beginning to sing, its first stable notes crystallizing out of a chaotic, fuzzy symphony of non-commuting coordinates, creating from pure algebra the substance that would eventually build stars and planets. But what if the very mathematical nature of these laws and the discrete properties of particles are not fundamental truths about reality, but simply the underlying architecture of a system? This brings us to one of the most controversial and philosophically challenging ideas on our list, the simulation hypothesis. The core proposition is as startling as it is simple. Our universe, with all its richness and apparent history, might not be base reality. Instead, it could be an incredibly sophisticated simulation, a kind of cosmic virtual reality running on a computer of unimaginable power in a parent universe operating under different, truer physical laws. This isn't just a plot from a science fiction movie. It's an idea that has been seriously considered by philosophers and even some prominent technologists and physicists. The argument often begins with a projection of our own technological trajectory. If human civilization continues to advance without destroying itself, we might one day develop the capability to run vast, realistic simulations populated by conscious artificial beings. If such a future is possible, then the number of simulated minds could vastly outweigh the number of biological original minds. Therefore, statistically speaking, if you are a conscious being, the odds are far greater that you are living inside one of these many simulations rather than in the original, base reality. From this perspective, the features of our universe that physics struggles to explain suddenly appear in a new light. Why are the laws of nature so perfectly described by mathematics? In a simulation, the laws of physics would be the code, the algorithms and subroutines that govern the behavior of the simulated environment. The mathematical nature of reality wouldn't be a mysterious, profound truth. It would be a necessary feature of its programmed construction. The universe behaves mathematically because it is mathematics executed on a cosmic scale. Furthermore, the simulation hypothesis offers a potential explanation for one of the deepest puzzles we've encountered, the apparent quantization of the universe. Why is energy transferred in discrete packets called quanta? Why do particles have fixed specific properties like mass and charge coming in identical types? In a simulated reality, this makes perfect sense. Computation is fundamentally discrete and finite. A computer, no matter how powerful, has limited processing power and memory. It cannot render a truly continuous, infinitely detailed reality. It must approximate it using discrete steps and finite pixels of information. The Planck length and Planck time, the smallest possible units of space and time in our physics, could be the literal resolution limits of the simulation, the pixel size and clock speed of the cosmic computer. The fact that everything is made of identical copies of fundamental particles could be a simple optimization technique, a way to save computational resources by reusing the same basic code for multiple objects, much like a video game uses the same tree asset in a forest. Even the bizarre, counterintuitive rules of quantum mechanics could be interpreted as features of this system. The probabilistic nature of quantum events, where a particle's properties are not determined until they are measured, could be a form of procedural generation or lazy loading. To save processing power, the simulation might only calculate the precise details of a system when it is being observed, leaving it in a fuzzy, undefined state until that moment. The phenomenon of quantum entanglement, where particles remain connected across vast distances instantaneously, could be a reflection of non-local variables in the code, a shortcut that bypasses the normal rules of the simulated spacetime. Of course, this idea is fraught with philosophical and scientific difficulties. It could be argued that the simulation hypothesis is ultimately untestable and unfalsifiable, placing it outside the realm of proper science. If the simulation is perfect, how could we ever detect the seams? Proponents, however, suggest that even the most sophisticated program might contain glitches or limitations we could potentially observe. Perhaps there are rounding errors in extremely precise calculations, or strange statistical anomalies in high-energy particle collisions that reveal the underlying computational lattice. Some have even suggested that if the simulators introduced a backdoor, a cosmic Easter egg, we might one day find evidence of it. Whether one finds the simulation hypothesis compelling or fanciful, it serves as a powerful mirror, forcing us to question our most basic assumptions about existence, consciousness, and the nature of reality itself. It reframes our search for a final theory not as a quest to understand the mind of God, but as an exercise in reverse engineering the source code of the cosmos. And in doing so, it transforms the first particles from fundamental building blocks of nature into the initial variables initialized at the start of the program, their properties not written in stone but in the logic of their creation. But beyond the stark digital logic of the simulation hypothesis lies a theory of breathtaking mathematical beauty, one that seeks not to simulate reality but to redefine its very geometry from the ground up. This is Roger Penrose's twistor theory, a radically different approach to understanding space, time, and the particles that move within it. While most of physics builds from the concept of a spacetime continuum, a stage with points and events, twistors flip this entire narrative on its head. In this framework, spacetime itself is not the fundamental starting point. Instead, it is a secondary, derived concept that emerges from a more primitive reality, a network of relationships between these enigmatic objects called twistors. So what exactly is a twistor? Imagine you're not looking at the path a particle takes through space and time, but at the entirety of its journey all at once, its entire world line. A twistor is a mathematical object that elegantly encodes this holistic information. It represents not just a point in space, but a light ray, a direction, and a spin. In a very deep sense, twistors are the fundamental building blocks of light and null rays, the paths that light itself travels. The crucial shift in perspective is this. In standard physics, we start with a spacetime point and then ask what particles or light rays are present there. In twistor theory, we start with the light rays themselves, the twistors, and the familiar arena of spacetime points emerges as the places where these twistors intersect. Spacetime is not the container, it is the consequence. This perspective has a profound and immediate payoff. It makes the bizarre laws of quantum mechanics feel far more natural. One of the great mysteries of quantum particles is their inherent spin, an intrinsic angular momentum that behaves in ways that are utterly alien to our everyday experience of spinning tops. In the standard approach, spin is a property we have to add to a particle living in spacetime. But in the twistor view, spin is not an add-on. It is absolutely fundamental to the twistor itself. The twistor's geometry is its spin. This means the quantum weirdness of spin, with its half-integer values and probabilistic nature, is baked into the very foundations of reality from the start, not awkwardly bolted on later. A spinning particle isn't a point-like object that happens to spin. It is a twisting, dynamic element of the geometric fabric itself. For the origin of the universe's first particles, this offers a radically different creation story. In the high-energy forge of the Big Bang, the concepts of distinct points in space and moments in time would have been ill-defined or perhaps even meaningless. Twistor theory is perfectly suited to describe such an environment because it doesn't rely on those concepts to begin with. The early universe would have been a seething, hot plasma of twistor relationships, a vast, interacting network of primitive light-like entities. The first stable particles to emerge, electrons, quarks, photons, would not have been born from the cooling of fields in space, but would have crystallized as particular, stable patterns within this twistor network. Their properties, their spins, and their charges would be determined by the specific way these twistors wove together, a cosmic knot tying that gave rise to substance. This framework provides a powerful new way to understand the fundamental symmetries of nature, those deep mathematical regularities that dictate how particles interact and that were set in stone during the universe's first moments. The most profound of these is conformal symmetry, an invariance under transformations that preserve angles but not necessarily distances. In the extreme high-energy conditions of the Big Bang, physicists believe this symmetry would have been perfect. Twistor theory inherently loves conformal symmetry. It is the natural language for describing it. This suggests that the twistor network of the early universe was a realm of pure angle and relationship without a fixed notion of scale. The emergence of particles with mass would then be directly linked to the spontaneous breaking of this perfect conformal symmetry, as the twistor network settled into a specific configuration that introduced a fixed scale, the mass scale, into the cosmos. In this view, the first particles gained their substance not by interacting with a Higgs field, but by the very geometry of the twistor universe selecting a preferred scale, freezing a moment of perfect symmetry into the diverse, massive world we inhabit today. Now, as we've ventured from vibrating strings to cosmic holograms, we arrive at a theory that is perhaps the ultimate in radical simplification. What if the most fundamental particles in nature, the electron, the quark, the photon, aren't particles at all? What if each one is, in fact, a universe in its own right, an entire cosmos curled up into a space so tiny it defies imagination? This is the breathtaking premise of the micro-universe, or world as a particle hypothesis, an idea that completely redefines the meaning of fundamental and turns the entire cosmos into a magnificent fractal reality. To grasp this, let's scale down the cosmic perspective to an almost absurd degree. We know that our universe is populated by structures within structures. Planets orbit stars, stars gather into galaxies, and galaxies cluster into immense superclusters. But what if this pattern doesn't stop at the level of electrons and quarks? What if it continues inward? In this view, an electron isn't a point-like elementary object. Instead, it is an entire, self-contained universe operating under its own physical laws, but existing on a scale billions of times smaller than an atom. From our macroscopic perspective, this micro-universe's incredibly complex internal dynamics manifest to us as the simple, stable properties of a particle: its mass, its charge, its spin. We are not seeing a tiny ball. We are seeing the external signature of an entire cosmic dance happening in a realm we can never directly access. This idea finds a fascinating, though speculative, foothold in the mathematics of black holes. As we discussed with the black hole electron hypothesis, there's a remarkable numerical coincidence. The estimated radius of an electron, if it were a black hole, its Schwarzschild radius, is on the same order of magnitude as its classical electron radius. While this doesn't prove anything, it opens a door to a profound possibility. The event horizon of a black hole is a one-way information membrane. What happens inside is forever hidden from the outside universe. Now imagine a primordial black hole formed in the first instance of the Big Bang, so tiny that its mass is only that of an electron. From our perspective, this object would have the mass and charge of an electron. And because its internal workings are hidden behind its event horizon, we would never be able to peer inside to see the complex universe that might be unfolding within. It would behave, for all intents and purposes, exactly like the fundamental particle we observe. This transforms our view of the early universe and the origin of the first particles. In the unimaginable density of the Planck epoch, the fabric of spacetime would have been frothing with quantum fluctuations, potentially pinching off tiny regions of space that could collapse into micro black holes. But what if they didn't just collapse? What if, due to the extreme physics of that era, some of these pinched-off regions stabilized not as singularities but as self-sustaining baby universes? Each one would have its own Big Bang, its own expansion, its own evolution, all happening at a scale trillions of times smaller than a proton. The energy required to create such a micro-universe could be balanced by the gravitational energy of its expansion, following the same something-from-nothing logic of the quantum fluctuation models, but on a microcosmic scale. The first particles wouldn't have been created, they would have been born, each one a cosmos in its own right. This leads to a staggering and deeply recursive vision of reality, a cosmic fractal. Our entire observable universe, with its hundreds of billions of galaxies, could itself be a single fundamental particle, a quark or an electron in an immeasurably larger universe. And within every particle that makes up our bodies and our world, there could exist an entire universe teeming with its own galaxies, stars, planets, and perhaps even life forms who are themselves made of particles that are micro-universes. Reality becomes an infinite regress of worlds within worlds, a structure with no top and no bottom, where the concept of a true, fundamental level of reality dissolves into an endless chain of cosmic containment. The implications for the laws of physics are equally profound. Why do we have the specific constants that we do? In this fractal multiverse, the laws of physics in our universe might not be fundamental. They could be the emergent, low-energy properties of the internal dynamics of the particle universe that we reside within. The mass of an electron in our parent universe would determine the total mass energy and thus the fundamental constants of our entire cosmic domain. This provides a potential mechanism for the anthropic principle. We don't live in a specially tuned universe in a vast multiverse of possibilities. We live in a universe whose laws are an inevitable consequence of the properties of the particle that became our cosmic egg. The first particles of our history had their properties because they inherited them from the physics of a larger world, and they passed on a derived version of those laws to the micro-universes thriving within them. This idea doesn't answer why any reality exists at all, but it transforms the question of fine-tuning from a cosmic mystery into a matter of cosmological inheritance, a story of physical laws being passed down through an infinite generations of universes. But what if the smooth, warping fabric of space-time described by Einstein is not the final word? What if, at the very tiniest scales, reality is not a continuous sheet, but is instead built from a finite set of geometric building blocks, much like a cosmic Lego set? This is the core idea behind causal dynamical triangulation, a compelling and visually intuitive approach to solving the problem of quantum gravity that offers a radically concrete picture of the universe's first moments and the emergence of the first particles. The central challenge CDT aims to solve is the profound incompatibility between general relativity, which describes gravity as the smooth curvature of space-time, and quantum mechanics, which governs the probabilistic, fuzzy world of the very small. When we try to apply quantum rules to gravity itself, the mathematics breaks down, producing nonsensical infinities, particularly at the high energies of the Big Bang Singularity. CDT sidesteps this problem by proposing that spacetime itself is not fundamental. Instead of a smooth continuum, it is constructed from tiny, fundamental pieces. The approach is triangulation because it uses the simplest possible geometric shape in any dimension, the triangle. In 2 dimensions, these are flat triangles. In the 4 dimensions of spacetime, the building blocks are 4-dimensional analogues of triangles called pentachorons or 4 simplices. The process is like a cosmic computer graphic simulation. Theorists begin with a vast number of these identical, simple building blocks and then glue them together along their faces, following specific rules. The most important rule is that the construction must respect causality, the principle that cause must always precede effect. This means the triangulation must have a well-defined time direction at every point. You cannot have closed time like loops where an event could cause itself. This causal rule is what gives CDT its name and prevents the bizarre time travel paradoxes that can plague other theories of quantum gravity. By assembling space-time in this way from the bottom up, CDT aims to show how the large-scale, smooth universe of general relativity naturally emerges from the random connections of these microscopic geometric pieces. The magic happens when you let this process run. You don't design the universe, you allow it to grow. In computer simulations, physicists start with a random soup of these geometric building blocks and let them connect according to the rules of causality and quantum probability. At small scales, the resulting structure looks wildly chaotic and crumpled, a jumbled mess with no discernible dimensionality. This is the quantum foam we've discussed before. But as you add more and more blocks and look at the larger structure, something astonishing happens. The chaos spontaneously gives way to order. The simulation consistently produces a smooth, four-dimensional universe with 3 dimensions of space and 1 dimension of time. The familiar geometry of our reality emerges all on its own from the random assembly of tiny pieces. This is a profound result. The dimensionality of our universe might not be a pre-written law but a phase of matter, a natural and stable outcome of quantum gravitational dynamics. So how do particles fit into this geometric tapestry? In CDT, particles are not foreign objects inserted into space. They are excitations of space itself. Think of the triangulated spacetime as a vast crystalline lattice. In any crystal, like a diamond, you can have vibrations traveling through the atomic lattice. These vibrations are called phonons, and they behave like particles carrying energy and momentum. In a very similar way, the intricate network of geometric blocks in CDT can support its own vibrations. A specific, self-sustaining pattern of distortions propagating through the lattice. A twist here, a stretch there, would manifest in our large-scale perspective as a particle with specific properties like mass and spin. An electron could be one type of vibrational mode, a quark could be another. The first particles in the universe would have been the very first stable vibrations to arise and persist in the cooling, settling spacetime lattice as it transitioned from its initial hot, jumbled quantum phase into the smooth, four-dimensional geometry we know today. This framework provides a breathtakingly clear narrative for the origin of the universe. In the very beginning, there was no space and no time as we understand them. There was only a probabilistic foam of these fundamental geometric building blocks, fluctuating in and out of existence and connecting in every possible way. This is the true Planck epoch. Then, through a spontaneous phase transition, a sort of cosmic freezing, the blocks organized themselves into a structure that had a clear time direction and 3 extended spatial dimensions. This geometric condensation was the Big Bang. It was not an explosion in a pre-existing void, but the crystallization of spacetime itself. As this new, stable geometry expanded and cooled, the vibrations within it, the particles began to take on their definite properties, setting the stage for the entire history of the cosmos that followed. In the world of causal dynamical triangulation, the first particles were literally the first notes in the song of space, ringing out from the geometry of the newborn universe. And finally, we arrive at perhaps the most elegant and mind-bending proposal of all, a concept so profoundly simple that it challenges our very definition of existence. This is the null universe hypothesis, a radical idea that suggests the grand total of everything, all matter, all energy, the entire cosmos, adds up to exactly nothing. It's the ultimate free lunch, a universe born from a perfect and perhaps necessary zero-energy balance. To grasp this, we need to think about energy in a much broader way. We're accustomed to thinking of energy as a positive quantity, the energy stored in a battery, the energy of a moving car, the energy that gives particles their mass. But in Einstein's theory of general relativity, gravity introduces a fascinating twist. It can have negative energy. Think about it this way. If you want to break apart a gravitationally bound system, like pulling the Earth away from the Sun, you have to add a tremendous amount of energy to overcome their mutual attraction. This implies that the gravitational field itself, which holds them together, must have negative energy. The bound system has less energy than the same two objects would have if they were completely separated and at rest. The gravitational binding energy is negative. Now, apply this logic to the entire universe. Every single particle with positive mass energy is sitting in the gravitational well created by every other particle. The null universe hypothesis proposes that these two colossal sums, the positive energy of all matter and the negative energy of all gravity, cancel each other out with perfect precision. The total energy of the cosmos is zero. This isn't just a quirky accounting trick. It's a direct prediction that falls out of the mathematics of general relativity for a universe that is flat and infinite, which our observations suggest ours very well may be. This changes everything about the moment of creation. If the universe truly has zero total energy, then the question of why is there something rather than nothing transforms into how did this magnificent something arrange itself from nothing? The Big Bang wouldn't be a violation of energy conservation. It would be a spectacular rearrangement of a zero energy state. In the beginning, there was a fluctuation, a quantum event where the positive energy needed to create all the particles was perfectly balanced from the very first instant by the negative gravitational potential energy those particles generated by their mere existence. They are two sides of the same coin, forever locked in a cosmic dance of mutual cancellation. The first particles didn't appear in a universe. Their appearance was the simultaneous creation of both the positive mass and the negative gravity that defines the universe. This perfect symmetry could have been the fundamental rule that dictated the properties of those first particles. For the universe's total energy to remain zero, the creation of every quark had to be instantly accompanied by the precise amount of negative gravitational curvature. This requirement could have acted as a powerful constraint, a kind of cosmic rulebook that allowed only certain types of particles with specific masses and interaction strengths to condense out of the initial quantum foam. Particles that didn't fit this precise energy balancing act simply couldn't exist stably. In this view, the mass of the electron and the strength of gravity aren't arbitrary constants. They are the necessary values that allow the most stable, zero-energy configuration of reality to exist. The universe isn't fine-tuned for life, it's fine-tuned for equilibrium, and we are a fortunate byproduct of that profound and beautiful balance. From the fiery singularity of the Big Bang to the silent, ghostly drift of actions, from the cosmic hologram to the possibility of a universe born from nothing at all, we have journeyed across an incredible landscape of human imagination and intellect. These 30 theories are not just abstract ideas, they are a testament to our deepest, most persistent urge to understand where we came from. Each one represents a different path up the same magnificent mountain, a unique attempt to answer a question that has echoed through the ages: what is the true nature of existence? Whether it's the elegant vibrations of strings, the cosmic rebound of a loop quantum bounce, or the breathtaking possibility of a multiverse, every theory offers a different lens through which to view the dawn of reality. There is no single, settled answer yet, and that is the very beauty of this pursuit. The search itself, this collective, centuries-long project of curiosity, is what pushes the boundaries of science and philosophy, forever expanding what we believe is possible. Now we want to hear from you. Which of these visions of creation resonates most deeply with you? Does the sheer elegance of cosmic inflation capture your imagination, or do you find yourself drawn to the radical simplicity of the null universe? Perhaps the holographic principle or the simulation hypothesis makes you see everything in a startling new light. Share your favorite theory or your own wild speculation in the comments below. Let's continue this incredible conversation together. If your mind is buzzing with possibilities and you're hungry for more journeys to the edge of understanding, make sure to subscribe and hit the bell so you don't miss our next exploration into the mysteries of space, time, and reality itself. Thank you for joining us on this voyage to the very beginning of everything. Keep